One of the most interesting things about pure mathematics is the way that it can make connections between areas that appear to be different. This lecture is going to take a single theme in which we shall look at different areas and show how this theme connects them. The first clue that there is a connection between these areas will be in some numerical coincidences. And this is quite typical of the way some parts of mathematics proceed. Numerical connections are spotted, and then deeper justifications are sought to explain those connections. So let's begin with thinking about elections. My first graphic is meant to indicate the way that votes are counted in an election. So this is an election in which two parties, X and Y, are competing. And the thick black line is showing the progress of the count as the votes come in. So a vertical line in this diagram denotes a vote for candidate Y, and a horizontal line denotes a vote for candidate X. So this election begins with 2 votes for Y, 2 votes for X, a vote for Y, then 3 votes for X, and so on. And at the end of the election, the count is at this place in the diagram, and Y has won by a narrow head. What I'd like to focus on, however, is the way in which, from time to time, this thick black line, which denotes the progress of the count, will cross the diagonal line here, which is the line Y equals X. And when that happens, the two candidates have got equal numbers of votes. If we look at the beginning of the election, where the candidates are level pegging, we then might look at another place, and from this place to that place, candidate Y has never fallen behind candidate X. From this place to that place, candidate X has never fallen behind candidate Y. And the whole election is a sequence of regions where, first of all, Y is never behind, then X is never behind, then Y is never behind, and so on. And right at the end, there's a place where Y leaps into the lead. But I would like to focus on these interim parts of the count where one candidate is never behind the other. So let's have a look at one of those parts of the count where one candidate has never fallen behind the other. And it's elections of this particular type that I'd like to begin with. Now I'm going to call these Jones elections. The reason is that if X was the Jones family, then Y has kept up with the Jones throughout the election. So that's what a Jones election is. Y is never behind X, and the result of the election is a dead heat. Let's have a look now at some small electorates and the possible Jones elections that we can have with small electorates. So here is a Jones election with 4 voters only, and only 2 things can happen. In this possibility, candidate Y gets 2 votes, and then candidate X gets 2 votes. Whereas in this one, candidate Y got a vote, then X, then Y, and then X. And if you think about it for a little while, you will see that these are the only 2 possibilities with an electorate of 4. Let's have a look now at something just a little bit bigger, namely an election with 6 voters. Here things are slightly more complicated, and at this election, Y begins by taking 3 votes and then X 3 votes, whereas this one, for example, y takes 2 votes, x 2 votes, a vote for y, a vote for x. And again, it will not take you very long before you can check that there are no other ways in which 6 voters can lead to a Jones election. Let's now go to something even more complicated, an electorate of 8 voters. And here are the 14 different ways in which Jones elections can proceed. This is slightly harder to check, but it will not take you very long before you can convince yourselves that these are the only 14 Jones elections. Well, we could now take this to an electorate of 10, an electorate of 12. The electorate is always an even number, of course, because in a Jones election, X receives as many votes as Y, and so there must have been an even number of votes cast. So here is a table in which I've tabulated the different number of Jones elections for electorates with 2 n voters. So we just looked a moment ago at 8 voters, and there were 14 elections. If we'd looked at twice 5 equals 10 voters, we would have found 14 Jones elections. And if we'd gone to an electorate of 2,000, we'd have found that there would have been this number of different Jones elections. Well, that, of course, is far too large a number for you to check by hand. It is, in fact, quite a lot larger than the number of atoms in the universe. So that's the first area that I'd like to consider. We'll now turn to a completely different thing. On this transparency, you see a hierarchy, a company structure in a small company. So we have the president at the top of the hierarchy. Underneath him, there is a vice president for technical, a vice president for personnel, a vice president for finance, and they in turn have their own minions, in this case a secretary and a programmer, in the case of the vice president personnel, a lawyer and an administrator, and they in turn have their own underlings, and right at the bottom of the hierarchy we have the T-boy, various secretaries, and accountants. This hierarchy is very similar to this hierarchy. And this is a different way of representing relationships. So here the relationship is not that of being a subordinate, but that of being a special case of. So at the top of this hierarchy we have the subject mathematics. Subordinate to that we have the areas numbers, algebra and geometry of mathematics. They themselves have got different sub-areas. So for numbers we might subdivide into rational numbers and irrational numbers. We might subdivide algebra into equations and calculus, and so on. So here we have a hierarchy which is being represented by a similar diagram, but where the relationships in the diagram mean somewhat different things. The abstract thing that such a hierarchy might be represented by is a diagram of this type. So I've removed all the names on the nodes of the hierarchy, but this is the abstract object that might be called a hierarchy. Well, let's have a look now at some small numbers, small sizes of hierarchy. Let's look first of all at a hierarchy where the number of relationships is only 2 or 3. In these diagrams you see hierarchies with 2 relationships. So this one represents a boss, an underling and a slave, whereas this hierarchy represents a boss and 2 minions. The 5 hierarchies with 3 relationships are listed here, and at this stage you might be experiencing a sense of déjà vu. We've seen these numbers 2 and 5 before, And if in fact we now look at even larger hierarchies, this time with 4 relationships, we'll see that there are in fact 14 such hierarchies. 2, 5 and 14, we've seen those numbers before, and this is a clue that there might be a relationship between the Jones elections that we began with. Well, let's see in fact that there is a very close relationship. So here is a Jones election, and here is a hierarchy. And what I'm going to show you is that there is a very close connection between this Jones election and that hierarchy. The hierarchy represents the Jones election in the following way. The Jones election begins with 2 votes for Y, and that corresponds to starting at the top of the hierarchy and coming down 1 step and another step. And then there was a vote for X, that corresponds to going up. Then there was a vote for Y, we come down. There are now 2 votes for X, so we go up and up. And we can continue to do this following the Jones election: vote for Y, vote for X, vote for Y, vote for Y, vote for Y, vote for X, vote for X, vote for X, until we've traced the entire hierarchy. And in just the same sort of way, we might start with the hierarchy and reconstruct the Jones election. So these little geometrical tricks tell us that there's a precise relationship between the Jones election and the hierarchy. And it explains, of course, why those numbers 2, 5 and 14 have occurred in both places. Now let's look at something a little bit different. Let's start off again with a hierarchy. Here it is. And this time we're going to imagine that the hierarchy represents the relationships in a family. It is a family tree. At the top of the hierarchy we've got the most senior person in the family. They have 3 children. Those children in themselves have, in this case, 2 further children. This one's got 3 children, and this one's got 3 children over here. And what we're going to do now is represent this family tree in a different sort of way. Normally, to represent a family tree, we do it in the way that I've just illustrated. But there is another way to do it, in which we might focus much more on the primogenitor relationship, in which the relationship between a parent and firstborn is given prominence. So if we go back to this diagram now, I've drawn in thick black lines what the firstborn relationship is. So here's the firstborn child of this parent. Now, if all we know are the firstborn children of the parents, we will not be able to reconstruct the whole family tree. On the other hand, if we have also relationships which say what the siblings of each child are, we can reconstruct the family tree. And in this next diagram, I've drawn in horizontal doubled lines the relationship of being a sibling. So this horizontal line represents that this person in the family is the next sibling of this one. Here's the next sibling, and on the bottom line we've got sibling relationships between grandchildren. If we now remove all the original thin black lines, we're left with this diagram. And this diagram is quite enough in order to be able to reconstruct the whole family tree. Now I'm going to redraw this diagram so that the horizontal doubled lines, which represent siblings, are now drawn at a sloping down angle, more or less the same angle as the thick black lines were drawn. Now we have a diagram that is called a binary tree. It's called a binary tree because at every point in the structure there are two possible things that we might do. We might go down to the left by a thick black line, or down to the right by one of these doubled thin lines. And you can see that at some places in this structure there's only a choice of one thing to do. So here we can only go down to the right. Right at the bottom of the structure we can go down neither to the left nor to the right. And these structures are called binary trees. They're very important, especially in computer science, because they are one of the tricks whereby the data in large databases can be retrieved very quickly. Well, the construction that I gave, where we went from a hierarchy to a binary tree, is a construction that we can reverse. And so that tells us that binary trees are basically the same as hierarchies. And we can confirm that suspicion by looking at the numbers of binary trees with small numbers of nodes. So here you will see the 5 binary trees with 3 nodes. Thick black lines always come down to the left and double lines go down to the right. And there are 3 with 5 nodes. If we look now at binary trees with a larger number of nodes, we'll find, to not our great surprise I think, that there are 14 binary trees with 4 nodes. And this is because there were 14 binary trees, 14 hierarchies with 4 relationships. So there is another way in which these numbers, 2, 5, 14 and so on, relate different areas. Now, these numbers are called the Catalan numbers. They're called the Catalan numbers after a mathematician called Catalan. He was a Belgian mathematician who lived in the 19th century, and it was he who first made these numbers come to the eye of mathematicians. It's why I have denoted them by the letter C in an earlier transparency. I'd like to turn now to a different area in which the Catalan numbers occur, and that's arithmetic. On this transparency, we see some algebra, and in this line I've written A times A times A times A, B times. This is normally represented as A upper B, represented as A to the power B. But for typographical reasons, I would like to write A wedge B. So this simply means A times itself, B times. Now, one of the questions that beginners sometimes ask when they're introduced to exponential notation is whether it's the case that A raised to the power B and then raised to the power C is the same as A raised to the power B to the power C. And occasionally this happens. You can see here 2 to the power 2 is 4, 4 squared is 16, and that's the same as over here, 2 to the power 4 is also 16. But that's very rare indeed, and on the next line you'll see that 3 to the power 3 is 27, 27 cubed is 19,683, and that's very different from 3 to the power 27, which is this very large number. And in general, if we bracket a large number of symbols together with exponential operators in between them, we will get different results according to the different way in which we carry out the bracketing. Here are 5 different ways in which we might express 2 to the power 3 to the power 2 to the power 3. In this case, the brackets tell us that we are working out 2 to the power 3, which is 8, then 8 squared, which is 64, and 64 cubed, which is 262,144. Whereas down here, the brackets tell us that we're working out 2 to the power 3, which is 8, 3 to the 8, which is 6,561, and then 2 to that power, which is such a large number that I can't represent it on this diagram? Well, 5 different ways of putting together 3 exponential signs. That number 5 has occurred elsewhere in this lecture, and there is indeed a very close relationship between different ways of putting together exponential expressions and the different structures that we've seen so far. Here is a way of seeing quite readily that binary trees and exponentials correspond very closely. So here we have an expression which uses 1, 2, 3, 4, 5 exponential signs, and here is the binary tree that it corresponds to, and you can see that it does by looking at this piece of the diagram, where we can see that the b to the power c is a number that has to be computed first. That's what the tree is telling us here. And then that result, together with a, has got to be put together with an exponential operator. And then over here, we've got to work out d to the power e, and then raise it to the power f. And then finally, we've got to take the result that we got over here and raise it to the power what we got over here. And that is what is being indicated by those brackets. Well, I'd now like to turn to a different way in which we might see these Catalan numbers occurring, and it's in a card game. So what I'd like to do is go back to the question of Jones elections, and this time imagine that we're looking at a Jones election and we're in a polling station. And in the polling station there are 3 boxes, and in the first box there are some tokens, and when somebody comes into the polling station and wishes to vote, if they vote for Y, then they must transfer a token into the middle box, and another vote for Y would be this. And if they vote for X, then they have to transfer a token from the centre box to the final box. So if we track a Jones election now, here's another vote for Y, here's a vote for X, here's a vote for Y, we can see that this middle box is recording the lead that Y has over X. So a vote for Y, a vote for X, a vote for X, and a vote for X. I'd now like to look at what I've just done in a slightly more sensitive sort of way. Rather than just using anonymous tokens, I'm going to use numbered tokens, where we work out what's going to happen with tokens that we can distinguish. So there's token 1, token 2, token 3, token 4 and token 5, and we'll carry out a Jones election. So here's a vote for Y, another vote for Y. Here's a vote for X, a vote for Y, a vote for X, another vote for X, a vote for Y, a vote for X, and a vote for Y. And you can see that what's happened is that at the end of the election the tokens have appeared in an order a little different from the order in which they started. Well, I'm now going to imagine that we're going to play a simple game of patience. And in this game of patience we have playing cards 1, 2, 5, 3, 4, and we're allowed to move these cards one by one into this pile and then into this pile, moving only the top number of each pile. And the object of this game of patience is to get the playing cards in the order 1, 2, 3, 4, 5 in the left-hand side. Let's see whether we can do it. Well, of course, we know that we can do it because I just showed you in reverse how it could be done. So we'd move card 1 to here, card 2 to here, card 5, now card 5 to here, card 3 to here, card 4 to here, card 4, card 3, card 2, and card 1, and this game of patience will have come out. And it comes out, of course, precisely when the original order of cards was given by a Jones election. And so we can now tell exactly how many of these patience games will come out. In the case of 5 cards, it would have been 42, the 5th Catalan number. In the case of 4 cards, 14 orders of cards would have given rise to successful games of patience. And in fact, here are the 14 different ways in which the cards can be arranged in order to give rise to a successful game of patience. I'd like to turn now to yet another way in which the Catalan numbers occur. And it's an area of geometry. On this diagram, you see a hexagon. In fact, you see 14 hexagons. And each time, the hexagon has been divided into triangles, 4 triangles in each case. And the rule is just that you can draw lines in the hexagon from one vertex to another. And always when you do this, you can obtain a division into 4 triangles. As we see in this transparency, there are 14 different ways in which we can divide a hexagon into 4 triangles. Had I started with a pentagon, there would have been 5 different ways in which I could divide it into 5 triangles. 5 and 14 are numbers that we've seen before. They are Catalan numbers, and these triangulations do indeed correspond exactly to the different situations that we've seen enumerated by the Catalan numbers. Let's see why that is. So here we see an octagon. This octagon is divided into 6 triangles, and here we see a binary tree with 6 nodes. And these two correspond in the way that you will now see. What I've done is put inside every triangle of the octagon a node of a binary tree. And when 2 nodes are in adjacent triangles, I've joined them by either a thick black edge or a doubled lined edge, according to whether the triangle lies on this side of the original node or on that side. So this node has got triangles to that side and that side. This node has not got a triangle to that side because you go outside the octagon. It does have a triangle on that side, and this triangle has got triangles on this side and that side. So in this sort of way, from every triangulation one can produce a binary tree, and from a binary tree one can retrieve the original triangulation. So it's no surprise then that the number of triangulations into n triangles is the same as the number of binary trees with n nodes. Well, we've looked now at a large number of cases which are connected by these numbers, the Catalan numbers. And what I'd like to do in the rest of this lecture is say something about the Catalan numbers themselves. And I'd like to begin by giving a formula for the Catalan numbers and trying to explain how this formula arises. So we're going to go back to the interpretation of the Catalan numbers as the number of Jones elections. So here's the Jones election that we've seen many times before. And now we're going to code the Jones election by saying 1 means a vote for Y and -1 means a vote for X. And then if we just track this sequence of votes, we shall get this sequence of 1s and -1s. Now, we know that this is a Jones election, and therefore the lead of Y over X is never negative. And that means that when we add up these numbers, term by term, as I have done here, we shall get the lead throughout the process of counting. And this sum then, this running sum of the numbers 1 and minus 1, will never become negative. Well now, let's imagine that before the election begins, Y's mother comes along and casts a secret and illegal vote for Y. And we see that in this next piece of the diagram. Here's the extra vote for Y. And this extra vote for Y means that not only does he no longer fall behind, as up here, but his lead is always one more than it used to be, and therefore he's always ahead. So we have now a sequence of 1s and minus 1s with an extra plus 1, where the sums always stay positive. Well, let me now give you the plan that we're going to follow in working out a formula for the Catalan numbers. Here it is, in a number of steps. What we've just seen is the Catalan number is the number of sequences of n plus 1 ones, because there was an extra vote, and n minus 1s, where the sums, as you add them up, are always positive. So we've recognized the Catalan numbers already by this property. Now we want to find out, therefore, how many sequences of n plus 1 ones and n minus 1s have this property. Here's the plan. First of all, we're going to find the total number of sequences with n plus 1 ones and n minus 1s. Then we're going to divide that set into families of equal size. Family size that for the moment I shall call Bn. Now, since all the families have got the same size, there will be in all An divided by Bn families. And then finally we're going to prove that in every one of these families there's one sequence only which has got this positive cumulative sum property that characterizes the Jones election. So having proved that, we're going to be able to deduce that the number of these Jones sequences is the number of families, and therefore the Catalan number is An over Bn. So let's now carry out the different steps of this proof. So first of all, we'd like to find out how many sequences of n plus 1 ones and n minus 1s there are, and we don't mind at this point just what the cumulative sum property is. So how would we do this? Well, a choice of the minus 1s will tell us what the entire sequence is. Because once we've picked the minus 1s, the places where the minus 1s occur, we will have the entire sequence, because the plus 1s have got to go into the places that we didn't choose. So the total number of these is just the number of ways of picking n positions out of a possible 2n plus 1. Now mathematicians call this number 2n plus 1, and they denote it by this symbol. So this is the number of sequences with n plus 1 ones and n minus 1s. There is in fact a formula for this, and I shall return to that in a little while, but this tells us that An is this number 2n plus 1 choose n. So that's the first step of our program for working out a formula for the Catalan number. Let's now look at the next step, which is to divide this collection of sequences into families. So we're going to define families in the following way. A family is going to consist of a sequence and all the other sequences that you can get by reading it cyclically. Here's what I mean. Here's a sequence of 3 minus 1s and 4 plus 1s of 7 symbols in all, and the different ways of reading it cyclically occur here. So here's the original sequence, 1 minus 1 minus 1, 1, 1 minus 1, 1. This next sequence is obtained by starting the first sequence in the second place. So it goes minus 1, that's that one, minus 1, that's that minus 1, 1, 1, those are those two ones, minus 1, those two, 1, 1. And when we get to the end, we've got to loop back to the front, to this one. This sequence is obtained by simply starting here and reading along here and then back to the front. So in this way, we can get 7 different readings of this sequence, and they comprise a family. So our sequences are going to split into families all of size 2n plus 1, according to the different ways in which we can start reading any one of these sequences. So those are the families, and our final step is to prove that in every family there's one sequence only with the Jones property, that the cumulative sums stay positive. And that's done like this. Here is a typical sequence of 1s and minus 1s. I think there are 7 minus 1s and 8 1s in this sequence. And here are the cumulative sums. And you'll see that this is not one of the sequences that we want, because the cumulative sums are not all positive. However, if we look at the place where the smallest, most negative number occurs, that's minus 2, both here and here, and we start reading this sequence from just beyond that place, so start reading from here, we shall go 1, 1, minus 1, 1, 1, 1, minus 1, minus 1, minus 1, and so on. And the sums are 1, 2, down to 1, 2, 3, 4, 3, 2, and so on. And this sequence of sums will always be positive. Now, it's not difficult to see that that rule that I gave for starting the sequence in the place following the last most negative number will always lead us to a sequence where the sums stay positive. And so we've now calculated all the different steps of the proof, and we can deduce that the Catalan number is the number of sequences divided by the family size, and that number, as I mentioned before, we can now give explicitly because there is a formula for this 2n plus 1 choose n number, and here 2n exclamation mark is pronounced factorial n, and it is short for 1 times 2 times 2n, all those numbers multiplied together, and likewise n factorial is short for 1 times 2 times 3 times 4 up to n. So there is a formula for the Catalan number. Well, that was a very multiplicative formula. I'd like to end this lecture with 2 numerical facts about the Catalan number, one of which is an additive fact, and I'm going to leave to you as a homework exercise to check. If you look at this table, you'll see that every row in this table is obtained from the previous row, and the rule is this, that to obtain any row, you just add up the numbers in the previous row. So let's look at the last row. That 1 is this one. The 7 is 1 plus 6. The 27 is 1 plus 6 plus 20. To get 75, we add in the 48. To get 165, we add in the 90. And we just go through the previous row, adding up the terms, until we get to the last place. And then we must duplicate the last number that we found. Every row in the table is found in that sort of way. And now, looking at the diagonal of this table, you will see the Catalan numbers. Exercise for you, try and work out why this is. So my final piece of mathematics is a question about when the Catalan numbers are odd numbers. If we look at this table of the first few Catalan numbers, they go 1, 2, 5, 14, 42, 132, 429, we see that the Catalan number is odd when n is 1, it's odd when n is 3, it's next odd when n is 7. And as a matter of fact, if you continue that table, you'll find that it's odd next when n is 15, then 31, 63, and so on. And in general, the Catalan number is odd when n is a power of 2 minus 1. So here is the general rule: Cn is odd when n is a power of 2 minus 1. The question is, why? Well, there are many ways in which we might address this question, because we know many descriptions of the Catalan number. But I'm going to use the description in terms of binary trees. So, let's go to this question: when is the Catalan number odd? And the first observation is that binary trees often come in pairs. Mirror pairs, I shall say, where if here is a binary tree, we get another related to it by just switching around the left piece and the right piece that hang from the top piece. So we get another binary tree, which will quite often be different. So that's what I mean by a mirror pair. Binary trees often come in pairs like this. Now, let us suppose that the Catalan number is odd and try and work out the consequences for n. So our supposition is that the Catalan number is odd. And the first deduction is that the number n must be odd. And the reason is in this little box here. If the Catalan number was even, then the trees would have a node at the top, and then n minus 1 nodes which were distributed between the left and the right parts. Well, if n is even, n minus 1 is odd, and you couldn't have equal numbers in the left part as in the right part. And therefore, when n is even, a tree and its mirror are always different. So when n is even, the trees come in pairs, and the Catalan number would necessarily be even. So now we know that n is odd. Now we can carry out this argument even when n is odd, and here is what it tells us. It tells us, in fact, that this Catalan number, the Catalan number for n minus 1 over 2, must always be odd. The reason? Well, which trees here come in mirror pairs? Those in which that piece is not equal to that piece. So we can forget about all of those in investigating oddness. The only thing that matters are the trees which do have L equal to R. And how many of those are there? Well, that's just a matter of how many trees we can put in this part of the diagram. So that would be a tree with 1/2 of n minus 1 nodes, and the number of such trees is this Catalan number. So if this Catalan number is odd, so must that be. Well, now we've reached a common situation in mathematics. We've reduced our problem to a smaller one. And because we know that this Catalan number is odd, we can now repeat the argument, and in repeating the argument, we shall find on the way that n minus 1 over 2 is odd, and that's this statement, and that the Catalan number for m minus 1 over 2 will also be odd. And then we can deduce that m minus 1 over 2 is odd. And we can carry on in this way until we've reduced the subscript down to 1. And so what we find is the following rule for determining whether the Catalan number is odd. It must be that if we repeatedly subtract 1 and divide by 2, we shall only get odd numbers. As you see in these calculations here, if we start from 63, Take away 1 divided by 2, 31. Take away 1 divided by 2, 15, and we will reach 1. And that will tell us that C63 is odd. On the other hand, if we start from 111, we will take away 1 divided by 2, take away 1 divided by 2, and eventually we shall get to an even number. And that will tell us that this Catalan number cannot be odd. Well, we've seen a lot of things in this lecture. We've seen the way that the Catalan numbers connect different scenarios, and we've seen some properties of the Catalan number. We've seen these different things that it connects, and we've seen a formula for the Catalan number. So I hope that you now feel enthused enough to go away and play with this very fascinating sequence.